Okay, let's take a look at another beam question, which is very typical of the kind of thing that you'd likely to see on the 3A1 provincial exam or indeed a college final exam. So in this example, we've got a beam that's 20 metres long and it rests on a support at each of the extreme ends of the beam. And in this example, all it's carrying is a uniformly distributed load of 50 newtons per metre over its entire length of 20 metres. There are no point loads here as indicated on the diagram. So the first thing I've got to do then is to convert that uniformly distributed load into our point load. And we can do that by saying that our point load is going to be equal to 50 newtons per metre and then multiply that by the distance of which it acts. In this case, 20. So 50 multiplied by 20 gives us 1,000 newtons that we can say is acting here at the centre of my beam. Now, how do I know it acts at the centre? Well, the centre of the beam just so happens to be the centre of the uniformly distributed section. That is, the uniformly distributed area is 20 metres that it covers, and the beam is also 20 metres. So divide that by 2, and we get the load right at the centre, that is 10 metres from the left or the right, depending upon how you want to describe it. Well, once we've done that then, we can now decide what the reaction forces are at R1 and R2. Well, hopefully you recognise here that if the supports that are at either end of the beam and we have 1,000 newtons directly in the centre, well then R1 and R2 must share that load equally because this is what we refer to as a symmetrically loaded beam. So we can say then that R1 is the same as R2, and that would be equal to 1,000 newtons divided by 2, which would give us 500 newtons at R1 and at R2. So once we know those reaction loads then, we can now go ahead and do our shear force and also our bending moment. So let's talk about the shear force first. Now, once again, it doesn't really matter here whether we go to the left or the right for our shear force because we're looking at that section XX as dead center. And if you go to the left, you've got one going up. If you go to the right, you've also got one going up, as well as, of course, those distributed loads. So once again, for argument's sake, let's just go shear force to the right-hand side of section XX, and I'll look at everything that's happening that way. Okay then, so what we're looking at first of all is if we go to the right of my shear force section XX, I've got my distributed load that is acting downward. Now, the distributed load, remember, is going to act in the centre of the section. And because we're only looking to the right now of section XX, that's only a distance here of 10 metres on my beam from this point over to that point. Well, 10 metres as a section, dividing it by 2, now puts my load right there at the 5 metre mark. And that load that we're going to see there is going to be our 50 newtons per metre multiplied by the distance over which it acts upon. It's acting over 10 metres and we've got 50 newtons for every metre, so therefore the load there is 50 multiplied by 10, which gives us 500 newtons. So going back down to my shear force equation here, I've got 500 newtons acting downward, so I can give that a positive number. We now move to the right of that, and we've now got R2, but R2, of course, is a support reaction, and it's acting upward. And if it's acting upward, we give it a sign of negative, and this is 500 newtons that we worked out earlier. Now in this example, plus 500 minus 500 gives us a shear force here of 0 newtons for our shear force. In other words, the beam is not in shear on the right-hand side. If we would have worked this to the left-hand side, we'd have got the exact same answer. So that first number there of 0 newtons, that here is just the first part of my question doing my shear force. We now need to go ahead and keep finishing it off, and this time getting the bending moment. So for the bending moment then, let's go the same direction as we went for our shear force and go bending moment to the right. Now the bending moment here is going to be coming from our little formula of moment is equal to force multiplied by distance. And that little formula defining what our moment is going to be is what we'll apply to get our bending moments. The only difference is we're going to add up the algebraic sum of our bending moments. And the two things to remember here about them when you add them together is that when we have bending moments that go clockwise, we give them a positive sign, and bending moments that go anti-clockwise, we give them a negative sign. So back down on my equation then, moving to the right of xx, the first load that I come to is this load that we set up earlier of that one at the 5 meter mark from xx of 500 newtons, which again we arrived at, which is 50 newtons per meter acting over a distance here of 10 meters. 50 multiplied by 10 gives me 500. Now, when we're taking the bending moments, we have to imagine that our section XX now is acting as the fulcrum or the pivot. So if I push down here at this green arrow here, indicating my shear force, or sorry, my bending moment force at 5 meters from XX, it would be acting in an clockwise fashion to the XX. And if it's clockwise, then we give it a positive number of 500 multiplied by the distance from this point here back to my fulcrum point here. Well, that distance is 5 meters, and that gives me my first bending moment. I'm now going to add this to my next bending moment. Well, moving to the right, we now get out to R2. And R2, in relation to my section XX, now acting as the pivot, this one would be turning my beam going that way, which would be anti-clockwise. And anti-clockwise bending moments get given a negative sign. So this one's going to be negative 500, which is our reaction force at R2, and now multiply that by the distance from R2 back to section XX, which is 10 meters. If we sort this out then, 500 times 5 gives me 2500, and then we can add this to minus 500 multiplied by 10, which is minus 5,000. 2,500 minus 5,000 gives me minus 2,500 Newton meters. That minus 2,500 Newton meters now is going to give me the indication as to whereabouts my bending moment is going. Now, if we look back up here, negative sign bending moments are going anti-clockwise. So we could write this answer as 2,500 Newton meters anti-clockwise, which means that up here my bending moment is definitely going in an anti-clockwise fashion with reference to XX. So our answer there is minus 2,500 Newton meters anti-clockwise for our bending moment, and my shear force part of this question is 0 newtons. So these are the two answers to this question. A great little one for a nice provincial type question. Hopefully this helped you out with this one. I'll see you in the next video.